Well, I'm really looking forward to this session, and I know that you're going to share with our guests who our first presenter is.
Absolutely. Thank you, Kevin. Today, our first speaker is Mandana Sarey, and she's assistant professor at the Technical University of Denmark. And she's in the section for indoor environment and a professor of daylight and lighting. Her research focuses on facade strategies, integrated lighting, and daylight strategies. And I'm particularly interested in her topic that she'll speak on. It's image-based characterization of view in virtual reality. Welcome, Mandana.
Thank you, Marta, for this introduction. Yes, I joined Technical University of Denmark in mid-2018, and I just wanted to point it out that this presentation is a lot about the students at DTU and their enthusiasm to learn about daylighting and lighting as much as it's about the view itself. Of course, view is a very important component of daylight. And with that, I would like to emphasize that if we want to have a holistic look at indoor environment, we have to look at the relation between view and visual environment with the other aspects of indoor environment being thermal, air quality, and acoustics. And only in this way we can meet this circle that we could understand how people react or respond to the different exposures that they get, including light, and how we can actually meet their needs within an indoor environment, being comfort, health, and performance. There were extensive talk about financial values of view yesterday at the Compass stage on affordability. So this is, of course, an important point to think about. But of course, benefits of view goes beyond that, and that is that view is actually a food for our eye. It supplies information about local environments, about the weather condition, about the time of the day. And these are all very important for our cognitive processes that we take when we are indoor. Of course, we know that in recent studies that view affects our perception of comfort indoor. So it has a significant effect on how we perceive comfort, visual comfort, and possibly the general comfort that we have in indoor environment. And last but not least, we know that it also affects our gaze behavior in indoor environment. I will go a little bit deeper into this. So in terms of perception, earlier on, well, this is a graph from one of the studies that I wanted to show, that we understood that, okay, if there are a nicer, more high quality view where including layers such as the ground, the landscape, and also the sky, then people would express less discomfort from their visual environment. But more interestingly, in the discussion of this publication, Linz very bluntly says that, well, what if glare is just an distraction? Larger focus on ergonomics of attention, vigilance, and visual communication, maybe that's the way to go. And there one suggests on the aesthetics of window design and facade composition. And this is very true. Glare is actually a distraction. In a series of studies that we did with a combined usage of luminance imaging and eye tracker back in the days when I was at EPFL. Well, for one thing, we could see that people look at the space in matters of seconds, or scan the whole space that they enter in a matter of seconds. And when we look at the fixation periods, or longer durations that they look at the space, we could see a clear behavior that they are attracted to the view over the whole subjects. These fixations mainly lay on the view when they are not focused on any task, but avoid glary conditions. We could also see that this behavior is different when we have different view types. For example, if there are more greenery and higher quality of view, then we have larger gaze shifts. So we shift between the different parts of the space in longer distances. Or if the view is very dull, like as you see in the middle one, then the picture on the wall becomes interesting suddenly, and we have at the same time longer fixations on these spots. And if there is no view, as we had in the third one, then basically the person just makes long fixation on the task or maybe the picture. So which characteristic of view is attracting or distracting? So while looking at the immersive space, or while immersing ourselves and looking at the gaze behavior and where people are looking at, how can we incorporate or understand the characteristic of view that makes this attraction and distraction in the view, and how can we later on include it properly in the analysis or understanding where people are looking, and how can that become an information. So here you can see that we can, from the photometric values that we have in these renderings, we can already give several information about the space. But how can we add to this, and how can we add the characteristics of the view? So this was the starting point of this project for us, which was funded by Biane Saxov, and it's one of the projects that I did since moving to DTU. And it was to understand this connection to the outdoor, the characteristic of views, but with the focus on selection of the fenestration systems. So it's not really focusing on the view quality itself and what it would mean, but it is with this end goal of selection of shading systems. And it's important to say that, as I said, the project is done with help of several students, and we have tackled different aspects that we should consider when including view, its characterization, into the simulation, into the VR, and into the technologies that we could use later on. For example, we have looked into the simulation of the shading systems in terms of how they scatter the rays of light and which resolutions we have to take into consideration when making these simulations, and how they would make a difference in terms of the simulation time and the end results that we get, and how later on, at the end of the project, how we can incorporate our findings into that. Then with a series of other students, Jaiki, Maria, and Signe and Jens, we have started using virtual reality for this. Well, there were several reasons to do that. First, the affordability of this. Then the possibility of integrating other environment, other parameters in indoor environment. Maria and Maria focused on audio environment, and we had a combined VR and audio environment in their setup. And of course, we thought that this could be a good use at the end, where we can incorporate all this information while the person is looking in the earliest stages of the design into the building and into what the indoor environment will look like. At the moment, we are running experiments, user assessments in reality. So we are moving from VR to reality with Emil, Sandra, and Sarah, where we are trying to replicate the same things in the reality and see if our findings are the same. So with the help of these students, we have looked into characterizations of view. And of course, there are a lot of, and recently more numerous studies that have been done on view and what it means in terms of the content, in terms of access, and the connection that we have to it, how to quantify them, and when it comes to shading or glazing, the view clarity, like how it would change the color or the image of the view. In our study, we wanted to, of course, incorporate all of this, but we wanted to be independent of the view quality itself, because the focus finally was on the shading systems or the fenestration systems that we will have, or the facade itself. So beside the view axis, we have also looked at other photometric relations or relations between different parts of the lit environment or the visual environment that could affect the view clarity, which is affected by the fenestration system. And those are color, color contrast, and complexity, at least for now. We have been looking on that. Quickly, just to say what they are about. In terms of color contrast and complexity, we have looked at the studies that have tried to come up with algorithms to look at this contrast and how the contrasts over the different parts of the image are seen or perceived. And the studies that have shown which one of the different algorithms that are there, or different metrics that are there for calculating this, are closer to our perception. And what this algorithm does is basically calculates a weighted contrast of one pixel in relation to its pixel around on different levels of resolution within the image, to give an understanding of what is the contrast that actually we're perceiving. Another one was complexity, that, how we understand the complexity in the image. And in that case, we have used a method which is using basically standard deviation of the image, and has seen that this has the highest correlation with perception of complexity in the image. So we have not developed anything on that, but we are just using this data. And in terms of connectivity or access to the view, we are using radiance and a ray tracing method that shoots rays from the point of view or where the person is assumed to be standing, and then tries to understand how much of that, many of those rays are subtracted. So these are some of the algorithms that we are using and trying to understand how they, if they would characterize the view for us in terms of attraction. And in all of the stages, we are looking at, we are concerned or very conscious about the field of view, where people are looking at, our limitations in movement of the eye and head, and etc. And the whole process of incorporating in the VR has many, many stages and routines that had to be incorporated. And of course, use of different tools and different methods, and making the methods better through the different projects that we have done. Just to name, we have used radiance for a lot of our visual environment, and audio for simulation of our audio environments, which in one of the projects we have looked. And then finally, we have done user assessment experiments using this method. In two of the studies, we had two smaller studies at the beginning, where we, in the first one, we incorporated with Schmidt-Larsen architects, and looked at two of their buildings with two different type of views, high-rise and low-rise buildings. And we had 13 different conditions that we looked at, and 15 subjects. Some of our findings was that the facade with least obstructions were preferable. There is a tendency to prefer a high-rise, modern and architectonic view as opposed to a low-rise landscape. And we could see that the view quality, if we rank the views in terms of quality, and the view connectivity had a stronger relation with more positive subjective assessments compared in comparison to contrast and visual complexity. We also had looked at the glass with the warm color tone, and this showed higher preference compared to the other conditions that we had. This allowed us to go further, and in another project which was done in an auditorium or an educational setting, we had a similar setup, but now incorporated the parameters related to the acoustic environment. And the subjects were able to answer the questionnaires within the VR environment, and there we could also see very interesting findings, such as participants were less satisfied with the view quality in the presence of higher background noise levels. The visual environment was less pleasant in the presence of higher background noise levels, and higher levels of contrast led to deteriorated perception of the room acoustics. So we found several relations between how the noise would affect our preferences in relation to view. And finally, we went back to our first hypothesis that we had and tried to use what we learned in a final experiment with, again, different shadings that we designed, thinking about the field of view, and over only two type of view quality. And of course, we have used we have tried to make the spaces as realistic as possible with as accurate photometry as values as possible. And in terms of contrast, so far we've seen that we've seen effects of achromatic and chromatic contrast, but in the case of achromatic contrast, this has not been a big effect. However, in the chromatic contrast, we've seen a larger effect. In terms of complexity, the same. We have seen effects on the lower p-value when it comes to the statistical analysis. However, again, the chromatic complexity had shown that it has a higher effect on people's perception of the view. We have seen the effect of different shading sizes and the effect of different view amount, or the amount of view or the connectivity on people's perception. And we have drawn some preliminary conclusions, such as the big blinds versus vertical louvers. They are preferred in a different way, or small blinds in terms, and big blinds in terms of connectedness, and how they are preferred in different ways. So finally, we have seen that we could actually use these measures to make this characterization. And for that, I'm thankful to my students. And I'm looking forward to see my next list of students, Emil, Sarah, and Sandra, who are working very hard at the moment to see that if they see the similar results in the reality. Thank you so much.